Hi, everybody. Welcome to another podcast of Making AI Possible. Today, I'm hosting with Dr. Issa Nesnas in collaboration with his work at Caltech and JPL. A little bit about the Center for Technology and Management Education here at Caltech. It's our premier executive education center where we host faculty, professors, industry experts, and then also researchers such as Dr. Nesnas from JPL to talk to different companies and different foundations as they come to campus to learn about best practices in artificial intelligence, systems engineering, and project management. All things that work very well when you're putting autonomous vehicles into space. So, here to talk about those autonomous vehicles is Dr. Issa Nesnas, who's a subject matter expert and not only space autonomy, but works closely with JPL, NASA Jet Propulsion Laboratory in Pasadena, and also Caltech. 25 years of experience in robotics and autonomous systems. He's led Robotics Mobility Group and Robotics Software Systems Group at JPL and contributed not one, not two, but three different Mars rovers and lunar rover concepts, along with his work with asteroid bodies. So I'm very excited to invite Dr. Issa Nesnas. Welcome to the show. If you could give a little introduction about your career, how you got here, and what you're currently working on, we'd be excited to hear that.
Great. Well, thank you, Nick, for hosting me on this podcast. Very excited to be here to share my experience and talk about some of these wonderful explorers that we send out into space. I started my career early on in robotics. Actually, I got interested in robotics at a very, very young age. I was a teenager in high school, and I got inspired by a show on TV, a sci-fi show called Buck Rogers. They had a little robot called Twiki, which really inspired the work I've done in robotics ever since. And at an early age, I set out to build my own robots, humanoid robots, not realizing how difficult and challenging that was. But that took me on a nearly 40-year journey, trying to understand the robotics, learn about robotics, and end up building robotic systems. I did start my career after I got my PhD in robotics. I did start in industry, and I worked in industrial automation for several years. And that was a wonderful opportunity because I was very fortunate to be able to work with leading companies in the US in industrial manufacturing. And the challenge there was how can we bring in flexible automation to industry? Meaning, how can we build an assembly cell that we can reconfigure to assemble anything from a Buick heating panel in the car to a Cummins engine to a camera, a Kodak camera at the time, and all do that with flexible automation and programming. And then my journey went into space after that. After JPL landed the wonderful Sojourner on Mars. And that was another inspirational moment that brought me down to Pasadena. And I started a career here at JPL and learning about space exploration and bringing my robotics experience there.
Excellent. I think that quintessential moment of what was it, 1997 with Sojourner. I remember as a kid seeing that too, and just even though I think we talked before the show, my only rocket experience was the Estes Rocket Club as a kid, and you had shared kind of your coaching experience that you've had with mentoring youth. But before we get into the nitty gritty of how you conduct autonomy on planetary systems, is let's understand the physical and operational realities of something that makes Mars, asteroids, or lunar surfaces so much more difficult and unforgiving than deploying AI here on Earth.
Yeah. So one of the things about the environment of space, it is different than Earth environment. It has unique challenges that terrestrial systems do not have to deal with. The first thing about space is the radiation environment. And that radiation environment really challenges the computation that we can use and also sometimes the sensing that we can use. So it does push you towards a grade of sensors and computers that would have to be radiation hardened or radiation tolerant, depending on where you go in space. Radiation is not all the same in space. So that's one of the particular challenge. Another very important challenge that most people may not be aware of is the thermal environment. Depending again where you go, the thermal swings could be so large and the thermal environment could be so extreme. So you have to may survive either very cold or very hot or both at times. And then the third thing is that you are interacting, especially when you go on the surfaces of planetary bodies, you are interacting with an unknown world. Now, there are places like the moon and Mars, we've been there multiple times. but there are always surprises depending on where you go. It's not all the same. But also you go into the outer, solar system, you go to places like Europa or even Enceladus. These are called ocean worlds. And these are places where the planetary bodies are covered with a crust of ice. We don't know the detail of their surfaces. We don't know their thermomechanical properties. So there is that uncertainty. And where the uncertainty comes in is when you have a robotic system having to interact on the surface of these other bodies. And sometimes not only just at the surface, sometimes you want to get inside these terrestrial bodies. So now you have to think about how do you penetrate through these terrestrial bodies to get to the interior. So all these things, the radiation, the thermal, and the surface and subsurface environments do present unique challenges. And to bring it all together, whenever we send an explorer out in space, that's it. Whatever hardware we put out, that's the only thing we can do, and we can't go fix it. It's out there, it's on its own. We can update the software, but we can't fix any hardware. So they have to work reliably and no opportunity to repair.
What would be an example of a hardware constraint? Because, here on Earth, we can go get the latest GPU that NVIDIA dropped, or, if you have the money. What are some limitations physically that you're up against?
Yeah. So a lot of times, one of the key things that's actually been driving space has been mass, because launch mass is expensive. If you're going to land that mass somewhere else, then you have to also worry about the landed mass, and you have to have a means to slow it down to get to the surface of where you want to when you go to. The other big challenge is power. How are we gonna power it? So a lot of times, you use solar energy. If you're gonna go very, very far from the sun, you have to use nuclear energy, and there's a limited amount of energy you're gonna get. And so energy, power energy, as well as mass are two big constraints that most terrestrial systems don't face the same challenges.
Excellent. So moving on a little closer to Mars. So when we trace how rover autonomy has evolved from, these tightly scripted, tightly ground control systems to this increasing capability of onboard decision making, what has that history looked like in respect to Mars specifically?
Yeah. So with Mars, I think there's a number of unique challenges with Mars. One of the things that Mars and Earth get close every 20, every 2 years, about every 2 years, 26 months. And that's the only time we can actually make the journey from Earth to Mars. But also because the way the Mars moves relative to Earth, there's another challenge, which is the communication. If we look at the light speed communication to Mars, we are talking about several minutes, 4 to 5 minutes, up to 20 minutes to talk from Earth to Mars. And that adds another dimension to the challenge of operating explorers on another planet. And because of that, then you have to really operate these rovers with a very limited or under the communication constraints that are governed by the physics and the orbital dynamics, the motion of the planets relative to one another. So this results in giving us a small window to talk to the Martian explorers, if you will. And that drives us, if we want to be very productive on the surface, it drives us to be able to endow these robotic assets with some autonomous capabilities. And that's been the trajectory that JPL has pursued even in the very early phases of its rover program. So if we look at Sojourner, which actually the rover that brought me to JPL, landed in 1997. It did demonstrate some autonomous capabilities of perceiving in front of the rover, assessing the hazards, and even avoiding the hazards. So there's been some basic rudimentary demonstration of that capability. But ultimately, that really grew and advanced significantly for the next rover, the twin rover, Spirit and Opportunities. And actually, Spirit and Opportunities had a significant amount of autonomous driving that was done for that mission. And these both rovers have been very successful over many, many years of exploring the red planet.
What was the reason for doing twin rovers at the same time?
Yeah, so there were prior Martian missions, during the era of faster, better, cheaper. that have suffered some challenges and were not successful. So the idea of doing a twin rover is to maximize the chances of one of them succeeding. And remarkably, both of them succeeded and beyond their planned exploration durations. People don't recall, but both twin rovers, which landed about a month apart, were designed to operate to drive, I think, a distance of a kilometer and operate for 3 months. And today, Opportunity still holds the record of about 48 kilometers on the red planet, and Spirit something on the order of 7.7 kilometers. So both of them far exceeded their planned duration and traverse distances. So they did quite a bit of exciting Mars exploration.
And so I'm hearing some reoccurring themes, which is autonomy being the core of autonomy being perception. Can you talk a little bit about the work that you've done in around perception and computer vision as it relates specifically to navigation?
Yeah. Perception is a key capability for not only Martian explorers or the rovers we put on Mars, but almost, all future autonomous explorers that we're going to send either to small bodies or to planetary surfaces. And the most common modality that we do perception with is really our cameras. Cameras are very, very powerful, but also cameras are very interesting because they're passive, they're not active. So they have a significant amount of durability, and a lot of them could be designed with a significant thermal range. They can operate at very low temperature as well as high temperatures, and you get a very high resolution information. So that makes cameras a very compelling choice for perception. It is not the only choice. There are other types of sensors, such as lidars, as well as radars, and we do these for a number of other missions. We haven't yet flown a surface LiDAR. That is a capability that would be important for the future. It has its advantages, but the technology is much less mature than cameras. And we can get into more details if you like regarding that dimension. But for going back to the cameras, so one of the key sensing modalities that we use is what we call stereoscopic vision, which are two cameras that are calibrated. And from those two cameras, we can generate a 3D perception of the environment. So, and that's important because it brings 3D situational awareness to the rover to be able to make decisions about how it should move.
Now, being lucky to have heard some of your seminars and some of your talks, you've talked a lot about the process of training the model. And
Mhm.
understanding that a lot of our audience are folks who work in AI and machine learning, could you talk a little bit about, say, for example, how perseverance, the process of going, X amount of distance, what was used to train that? How do we know it's making smart decisions?
Yeah, yeah. So the capabilities that we use and autonomy in general is a spectrum of capabilities. And the way we implement autonomy, it could either use classical techniques, which are physics-driven techniques, or we could use all the way data-driven techniques, which are all the AI, or we can use somewhere in between. And our past rovers have actually relied on physics-based techniques to perceive its environment, assess its hazards, and make decisions. But as with the advancement of more data-driven techniques, we are starting to incorporate more and more AI and machine learning capabilities in our navigation. And you may ask, so why do you really need AI? So one of the key opportunities I see in bringing in more AI is the fact that there is uncertainty in the environment that results from the challenges of that environment. And data-driven techniques are very good at ingesting and dealing with that uncertainty and making decisions. Now, the big concern about it is how do we verify and validate that it may not hallucinate or it may not take the wrong decision? And this is the way that comes into the way we architect the systems. So you can use these more predictive techniques and techniques to handle the uncertainty, as long as you have a way to check that the decision is a safe decision. And this is how we've been able to incorporate AI in a safe manner. So some of the ways we've incorporated AI, for example, has been in the area of terrain classification. If I'm driving on Mars and I want to understand the different terrain types, a rocky terrain, a sandy terrain, I can use AI techniques because it's a lot easier to use that data that I've collected, train it based on either subject matter experts or scientists, and then be able to deploy it to tell me, is this a sandy or rocky terrain, which makes a difference because if I go in the sandy area, I may have a higher chance of getting stuck in it. A rocky area, I'll have better traction. And that's one technique. But another technique comes into the fact that if I have, occlusions from my perception, I may not be able to see certain areas because, light travels in straight line and certain things may be occluded. So I can use AI techniques to help me, fill in the gaps. I can use AI techniques to assess whether a particular terrain geometry is hazardous for a rover to drive on or not. But I can also use physics-based techniques. And that depends on the complexity, not only of the terrain, but also on the mechanism of the rover that you're trying to drive over that terrain. So there are multiple ways where we can use this. Another way we can use AI techniques is in the way we assess the health of the system. So if I can monitor my telemetry or my data coming from the rover, then I can look for patterns that are off nominal, which could be very hard to describe in a classical way, but maybe may lend themselves more to data-driven techniques. So when we look at AI and machine learning, it is really a spectrum of physics-based and data-driven techniques. And there are limitations, of course, of the data-driven techniques we can talk about as well.
No, that was a perfect explanation. The word for me that stuck out was uncertainty because we see this in industry specifically around LLM-based systems. Giving a probabilistic output, non-deterministic system. How do you essentially avoid those? And that leads to the question: is when you're testing these, just as though we do in industry, how do you ensure that kind of the failures that you assumed were going to be successful don't bleed their way into the deployment? Essentially, like, were there any interesting edge case failures that you thought were going to work, but actually didn't?
Yeah, so one of the big challenges in building highly reliable systems, especially for systems that are safety critical, um, is what we call the long tail distribution. There are so many things that could go wrong. The probability of each going wrong is really, really small. But the way these occur is not because of one particular failure. Sometimes it's a confluence of multiple things that go wrong that can create a bad day. And if you study the failures of past missions and the failures of systems in general, especially safety critical systems, it's the fact that multiple things went wrong in some very subtle ways. And this is a particular challenge for all kind of techniques, including machine learning techniques, because there is a dearth of information to train networks on. And this is more challenging even for space applications because if I'm going to go somewhere new, nobody has been to this place. Let's take Enceladus as an example. In an ocean world, a new world for us. We may make assumptions or we may train something based on our biases or our understanding of that environment, and often we're wrong. And so, how do we combine we know physics holds everywhere, and we can rely on that, but also it's very challenging to model everything because sometimes the models are so complex that we revert to empirical models, which are not, first order physics derived. And then the data-driven techniques, we have a dearth of data. So we're kind of in between. And this is where, the challenge is in architecting systems that could be robust and resilient to operate in such environments. So it is still a challenge. And we are in the very, very early phases of really architecting autonomous systems.
Was there any behavior that surprised you from any of your field testing? I don't want to use the phrase emergent behavior, but I don't know, through the process of testing, you said, oh, maybe that's not a bug, that's a new feature of a capability. Anything that stood out?
Yeah, so the one I can think of, I mean, there's in our prototyping efforts, we do anticipate a large number of surprises because things are still being developed. But when we take sometimes our more mature systems, like our flight systems, some of the things that actually surprise us is comes from the environment we operate in. And I'll give you an example. When we were on Mars with the Phoenix lander, um, you would think that, scooping could be, how challenging could collecting a scoop sample be? But and despite studying the whole range of our understanding of the environment and the dynamics of scooping and depositing the scoop, the material ended up being far stickier than we imagined. And that presented a situation that made it challenging for the mission. Eventually, they were able to get the material into the instrument that they needed to. But this is just an example of the type of challenge that we face. Uh,
Yeah.
when we go to the moon and we're trying to operate in the lunar environment with sun low in the sky, we anticipate that's going to be quite a bit of challenges associated with the light and the
Mm.
interaction of the light with the terrain and the rover. And we try to imagine all possible things and consider our best understanding of those challenges. I also wouldn't be surprised that we'll get surprises or these planetary bodies always end up throwing a challenge at us.
Naturally. So that's a good segue from your work on Mars over to where you're currently working on lunar missions. Can you talk a little bit about what those look like on the other side of the moon?
Yeah, so I am working on a lunar mission concept, which is to go in and land at the center, near the center of one of the largest and oldest impact basins in the solar system. And the purpose of this mission is, and the mission concept is to collect samples and bring them to Earth through the Artemis astronauts. And the manifestation of the concept revolves around a vehicle that will land somewhere in the middle of that impact basin, collect samples along the way, traversing thousands of kilometers, and bringing those samples for the astronauts to bring back to Earth. It is a concept that was reviewed by the national academies through the decadal survey process and was selected or was ranked as the top priority for lunar exploration in the next decade. It is a very exciting mission that the science community has been interested in for the last 3 decades.
How does that process look like from you're thinking in your lab, you're thinking in your office, gosh, this would be a really cool autonomy play. What's the process to get, from that original conception of the idea all the way to winning top ranked qualification and then turning it into an actuality?
Yeah. So one of the things that JPL has is it's a depth and breadth of expertise in pioneering first of a kind missions. And this is no different than other things that JPL has done, but it also leverages a lot of the work JPL has done. So JPL has been on the Red Planet for decades and has operated vehicles for decades. And this new mission concept really extends the capability of roving on planetary bodies, but doing that with order of magnitude more distance and more speed than ever been done before. So it does leverage the depth and breadth of expertise of the organization, but also takes a next substantial step, all in the service of conducting compelling science.
Yeah.
So what is the best way to collect the science so we can further our understanding of the origins of the solar system? And the capability we talk about is an enabling for that science. And a lot of things are really driven by what are the scientific questions, the important scientific questions we need to answer, and what are these capabilities that enable that science.
Brief interlude for folks listening. If you do have a question for Issa, please drop it into the comments. Jen will and Stacy will tee them up and then we'll pepper them into this conversation. All right. So that being said, we've looked at the Martian surface, we've looked at the lunar surface. Tell us about asteroids and autonomy.
Yeah. So asteroids and autonomy, there's a very interesting and exciting opportunity to substantially advance autonomy for exploring small bodies. So I'm going to talk about small bodies in general. There's nearly 1 million small bodies in the solar system. And the number of small
And
bodies,
how would you define a small body? And because this is news to me.
yeah,
1 million small bodies in our solar system.
yeah. So anything like asteroids and comets, and there's different types, are in the class of small bodies. Asteroid belt is full of, asteroids that are, classified as small body. There are the formal definition of what is a small body versus a planetesimal versus a planet. That there's certain formal definitions that, somebody in the scientific field can better describe that. But they're generally much smaller bodies, a significant number of them. The larger small bodies, like Ceres and Vesta, um, we know a little bit more about. Some of the smaller ones, we don't know as much about. And of course, they're scattered all over the solar system, in the Oort cloud, in the asteroid belt. But there's a huge number of small bodies around Earth, which are called near Earth objects or near Earth asteroids. And the number is so large. But also, if we look at how many of these have we been able to visit, one way is you fly by them. The other way is you actually rendezvous with them, where you actually are targeting them and you observe them and study them for a longer period of time. You're not just crossing paths. And the number is, I think it's around 25 that we may have flown by, and only 7 or 8 that we actually rendezvoused with. So it's a very small number. Now, there's an interest in understanding and studying the population of such small bodies. And this is where lies the opportunity. There's a scientific challenge to study and explore these, but there's all limited resources. And we can't, it's very expensive to send a spacecraft to explore small bodies or to explore any place in the solar system. So what if we combine three things? We take the fact that these are very numerous small bodies. We take the fact that we have a growing, burgeoning small sat community, and we take advances in autonomy and AI and sensing. And if you combine those two, it poses a question, could we build a small satellite, small spacecraft that can go to and explore a small body with a high degree of autonomy on its own? Do we have the capabilities? So there's many, many challenges associated with doing that. The first thing you have to do is you have to design the spacecraft and build it, which is within the realm of some of the technologies we have today. A big thing to rendezvous with a small body is a delta V, and advances would be needed to be able to create a higher delta V. But there's even with the current capability of the delta V, there's a significant number, or there's a notable number of small bodies we can rendezvous with if you're on the right trajectory. So the next question comes in, do you have the sensing and computing and AI and intelligence to be able to do everything you need to do with minimal human intervention? And the reason is, imagine if we can build small satellites, small spacecraft that can go to these and explore them and put different instruments and go to different places. That will open up the opportunity to understand the population, not individuals, but the population.
Mm.
And this is the concept that we put forward called DARE, which stands for Deep Space Autonomous Robotic Explorers, an idea of building a small spacecraft with highly capable computing that can use perception and machine learning and AI to take us on a trajectory to eventually rendezvous with, map, and then get down to the surface and explore the surface of that small body. And to be able to do that, there are a number of challenges. One of them is if you go to a small body, you may not even know what that shape is. You may not know how it's rotating or nutating, which is how does its rotation axis change. You don't know what the surface looks like. And then you have to interact with it because the gravity is not uniform, because that's going to be a non-uniform shape. So you have to discover, assess, build up that information, make decisions, and approach it without crashing into it, and then be able to take measurements, send them to Earth, and then figure out a way to get to the surface. So you have to land. And because it's such a low gravity, what you can do is you can bounce around the surface. So that's an easy way to move around small body. You can bounce around and then collect measurement on the surface. So you can collect measurements from what we call a hover point, a distance from that body, as well as get to the surface and then collect measurements from the surface. So there's a little video online that I can provide the link that describes that concept. And what we envision could be possible. And this is something that could be possible within the next, 5 or so years. And
Yeah.
I think there's been sufficient advances in a number of areas that a lot would allow us to push that forward.
And I'm taking it DARE as in Deep Space Autonomous Robotic Explorers is Dare Mighty Things from
It is.
JPL tagline.
It is our tagline, which is "Their mighty things together," bringing the best of, JPL, academia, and, key partners in industry to actually
Mhm.
enable such things. It's really the whole point is there are challenges out there waiting for us in space, and we are limited by two things: the resources we have and our imagination. And we can tackle those challenges collectively. And there's great opportunity to align a lot of the research going on in academia with
Mhm.
that going on at JPL, with that going on in industry, and push the boundaries of what is possible. It will take us, I want to emphasize that what I do describe is challenging, but this is precisely the type of challenges that we should be tackling, which are things that push us to to advance things in a way that would open up future opportunities.
Mhm.
And this concept, I may add, it was conceived as a stepping stone. The idea is we need to learn how to do autonomy in our backyard. Being able to, if we can go to these near Earth objects and explore them autonomously and master that, and then we can go farther in the solar system and go to places that are far more challenging and be able to do more remarkable things.
Mhm.
Can
Very,
learn. Yeah.
very well put and poetic too. All right, we'll get into a couple questions. So for in the next 10 years, what are your predictions? What are some of the things that make you excited?
A lot of things. So I think we're going to see a substantial increase in the exploration of planetary surfaces, in particular the moon. I think there's going to be a lot more people landing on the moon and also more roving on the moon. I do predict that to happen in the next 10 years. I also predict that people will push the boundaries on autonomous spacecraft and demonstrate more capable autonomous spacecraft, both in LEO as well as on the moon, as well as in deep space. Um, the other exciting thing that's happening is that there's an increase in the amount of computation that's becoming available. So one of the key things that held us back in the past is suitable computing for exploring space. And there's been advances in high performance space computers. There's been advances in battery technologies. There've been advances in solar cell technologies, and all these things would allow overcoming some of the challenges. Power and thermal will remain challenging. We can do more with more efficient computing. And then we have to find ways to overcome, these cha the environmental challenges. Yeah.
Right. Another question, how do you see autonomy being used for the search for life outside of our planet?
Yeah, so so for Martian explorer, so one of the places that people thought would be the one of the best candidates for searching for life has been Mars. It's been like that for many, many years. There are still places on Mars we haven't been to, the more challenging places. There are, and then of course there's the ocean worlds. And ocean worlds, these are these bodies I mentioned earlier, which are covered often with a crust of ice, and underneath that crust of ice that could be rather thick, there is, what is expected to be a liquid water ocean. And being able to get to those is extremely challenging. But this is one of the, best candidates in the solar system to look for, past or present life. And the challenge for future explorers is how do you get through a thick crust of ice? Where do you get the energy? How do you build a system that's robust to fighting its way through those ice? Sometimes these ice plates may move, they can crush you, they can destroy your communication infrastructure. So there's a lot of engineering that has to be done, but there's also a lot of intelligence that have to be exhibited by these explorers. And so there's plenty of opportunities to innovate and overcome. But these are very, very serious
Yeah.
challenges as well.
Well, I think that's a great place to end it with predictions and kind of some hope for the future. Um, Dr. Issa Nesnas, I can't thank you enough for joining us, and I know you have a busy schedule, so we really are grateful for the time that you've taken, and we are very excited to see the fantastic things that are coming out of JPL and Caltech.
Nick, thank you very much. It's a pleasure to be on your podcast.
Great. All right. Thanks, everybody. Until next month on Making AI Possible. All right. Bye bye.